students, once again regarding the motion of wave packets, I am presenting this video in terms of Schrödinger equation part 2, and this equation will be time independent case. So let's proceed. What is this time independent Schrödinger equation? Well, for that, to get the time independent version of Schrödinger equation, TIH, we took the potential energy as independent of time and just represent V equal to VR, only function of R, removing the time variable from the functional dependence. Using it, we use the method of separation of variables, where psi RT is equal to UR, and U as a function of R and F as a function of T, which is given by equation 1, and we'll use this method of separation of variables in the equation for time in the time dependent Schrödinger equation. So this is time dependent Schrödinger equations. Putting equation 1 in 2, we get an equation of this form. Since this is a partial differentiation, so this del T will affect only the time dependent part, that is F, and this nebulized core, which is space dependent part, will affect only on U part, this is U. So since V is also dependent on R only, so this VR is written like this, and ultimately we have equation 3 here. So this UR is coming outside because we need a partial differentiation. We use this psi has both U and F, and since U is independent of T, so definitely U will come outside of this differentiation. And the same is true for in case of nebulized core. Nebulized core U into F. So nebulized core psi means nebulized core, it will affect only on nebulized core. The nebulized core will affect only on U, and F will simply come out as a constant out of the differentiation. So equation 3 now. So dividing this equation by UT, UR and FT, we get an equation 4. So this UR will be cancelled by this UR, and it will be 1 by FT will be there. IS cross is already there. So IS cross by FT, del F by del T on the left hand side, and the right hand side, this UR FT will go since it is divided, and this FT will be cancelled by this FT, and so we'll left it 1 by UR, and only minus S cross square by 2 is there. So equation 4 is that we get by dividing equation 3 by UR FT. Next, since we see that this left hand side of this equation 4 is completely dependent on time, and this one is completely dependent on the space R, so definitely they must be equal to some constant, and then let us put that constant equal to capital E, and in that sense, taking only the left hand side of equation 4, that is this part is equal to capital E, so we'll have this equation I cos ft del F del T equal to E, and the right hand side will be equal to also E, and just rearranging the terms we get minus del H cos square twice and nebulous square U plus VR UR equal to UR. And now this 7, equation number 7, is nothing, it's a time independent Schrödinger equations. So we again arrive at the time independent case of Schrödinger equation with the help of method of separation of variables with the help of equation 1, and simply taking that potential energy is independent of time. Now we'll take care of this equation 5 also, which is taken to be temporal part of Schrödinger equation. So just rearranging that one against equation 5, we get del F by F, and then E by IS bar, IS cos del T, and integration. Since we think that the left hand side, you see that the left hand side is dependent only on time T, right hand side also right hand side, so there's no need of partial differentiation here. We simply dF by F, E by S cos by dt, and once we integrate this quantity, this will be log F, and this dt will be integration. After integration we get T, and C is a constant of integration, and we can put it as equal to C equal to 0, and in that case we will left with log Ft equal to capital E by IS cos T, and doing all this just removing the log term with the help of exponential, we get equation 10. So Ft equal to e to the power E by IS cos T and this is the temporal part of Schrödinger equation. So ultimately, going back to equation 1, where psi rt is equal to ur into ft, we can put psi rt equal to ur e exponential to the power e by I cos by t. We can put this like also minus I e divided by S cos also into t, because this minus 1 will give us I square minus this is plus 1 can be represented as a minus I square. So this I and I will cancel, so ultimately we will get e to the minus I capital E t divided by S cos. That can also be another. So with in this way we get time independent Schrödinger equation. And looking back at equation 7, this nebula square, which is representing the three-dimensional case, can be replaced by d square by dx square for one-dimensional case, or maybe d square by dx square. Since in that case r will be replaced by x, and this nebula psi is equal to del psi by del x. So one-dimensional form of Schrödinger equation is also possible. Now we see that time-dependent Schrödinger equation is simply gives the time evolution, while that time-independent Schrödinger equation is an eigenvalue equation. We will talk about later on this eigenvalue equations when we will talk about operators. And it is important to note that the time-independent Schrödinger equation is a solvable one, and for that we also need a well-known form of, we must know the form of potential also. And the solutions of the time-independent Schrödinger equation will be known as separable solutions, and that constants E, which is actually nothing but energy, actually is also known as separation constant. The idea of separable solutions is because we have separated out the time-independent part and get a eigenvalue equations which is easy to solve instead of the time-dependent Schrödinger equation, which is not an easy case to solve in a direct way. So we are left with time-independent Schrödinger equations, which will solve, will get the separable solutions, and these solutions will be incorporated with this factor, the temporal part of Schrödinger equation, or the temporal solution of Schrödinger equations, and to get the total wave function in this form, which is nothing but this equation 11. So with this u will be found from the solution of time-independent Schrödinger equations, and multiplying with that time-independent solution with this exponential form will give us the total time-dependent solution for Schrödinger equations. So these solutions coming out of that independent equation is nothing but they are simply known as stationary states, because they are stationary with respect to time. That means that if we consider a state, these states are nothing but they are having some definite energy, as well as that the wave function is also has a definite value depending only on r but independent of time. So that's why they are known as stationary states. And coming back to this thing that how we can prove it, we see that if we take the probability density of the time dependent wave function, we get an equation like this, and that exponential part where I is there, I will cancel out ultimately. This is minus and this is plus, this will give us 1, this exponential will give us 1. So ultimately u star and u will be left, and ultimately this is nothing but u modulus square. So we say that the time dependent part is replaced by time independent part, and that's why that once we get the time stationary states, we're having time dependence, we're having some definite value of psi depending on r only, and also energy depending we have constant value of energy also at the time. So we see that the probability is no longer dependent on time, and that's why it's stationary state. And also you can take it for the expectation value also, and expectation value for position is constant while regarding the stationary states, and also that momentum expectation value is 0. And this does conclude that in a stationary state actual motion cannot be interpreted, but still the stationary state has immense importance when we'll discuss time dependent general solution in terms of superposition of stationary states in the coming time. So stationary states are very important. It's because it gives us the solution coming out of time independent Schrödinger equation, and these time independent solutions are now, when incorporated with time dependent factor or exponential factor, we get the time dependent solutions, and we thus get into the time evolution of the system, quantum mechanical system. So, and also one thing that the time that the stationary state have definite energy can be proved from the time independent Schrödinger equations, which is nothing as an eigenvalue equation. We just for timing, let us remember that the equation of this form is nothing, is an eigenvalue equation where this cap is representing that Hamiltonian operator. We can say cap is given usually for operator representation, is operating on the wave function ux, time independent solution, that means, and this is giving us some value. So eigenvalue is, for in a nutshell, to say that if an operator appearing on a function give us an equation like this, where the functions where it is acting is not sensed, but only thinks that the operator is giving some value to that system. And this Hamiltonian operator is nothing but we can represent it by like this for one-dimensional case: h minus h cos square by twice m del square del x square plus bx. We're considering only one dimension. That's right, it's a Hamiltonian operator. And when we take the expectation value of this quantity, the expectation value is defined this way. It's a wave function, complex conjugate of the wave function on the left hand side, then the operator, and then the wave function, and it is integrated over the variable x. So this is the definition of the expectation value of this operator h. Now, since h, the operating on u, is nothing but it gets given by equation 30, it is eu. So this e is a constant thing, and it will come out, and that we are left with e into integration is u star u dx. U star u is nothing but this modulus u square. The integration will go out, and ultimately, since u square is nothing but psi square, it is a time dependent solution. This time independent solutions, as we have already get it in equation 12, u psi modulus square is nothing u modulus square. So in the same way, we are just replacing that thing here, equation 12 here, and since this is nothing but it is equal to 1 actually when we are integrated over whole space, so ultimately we are left with that expectation value of the Hamiltonian operator, or the total energy is equal to E. So this means that energy is derivable from the can be obtained as an expectation value from the Hamiltonian operator. And also we have these kind of things. H operator is for u, it is operating 2 times h cap u is giving us eu will come out again, it is h cap u, again h cap u will give us another e here, so e into that or e will give us e square u, and so modulus of h square, that means the expectation value of this Hamiltonian square is defined as like this: u star operator h square u dx. This is already given here. This is nothing but u square, and this u star u is nothing but modulus u square. So integration is here, and while doing after all this integration, since it's simply a normalization conditions, so this normalization condition would give us e square. So thus from a statistical point of view, the variance is defined as like this: this delta h square is equal to expectation value of h square minus expectation value of h square is equal to, in the both the cases, this is equal to e square and this is also equal to 0. So this confirms that separable solutions has the property that every measurement of total energy gives the same value, that the energy is constant, and there is also another reason that it's known as separation constant. So what we talked about, that for stationary state we have definite energy, is now proved in this equation after some kind of operator representation and a concept of eigenvalue, which will be later on cleared by incoming videos. But for the time being, with simple definitions and simple concepts, we can arrive at essence. So these are the assessments here. Assessment that arrive at the time independent case of Schrödinger equation. Then what is temporal solution? That is asking about FR, FT, and then also expression for it. And what is a stationary state? Very important. and the probability is independent of time, that is already we have shown this, and also that what is the time independent Schrödinger equation if we take the potential is of the form Vx. So hope that this part of video where we talked about time independent case of Schrödinger equation will help us to differentiate between time dependent case and time independent case. You can understand the time independent Schrödinger equation give us some solutions. These solutions, when incorporated with the time temporal part, will give us the time dependent solution of the Schrödinger equation, that is psi rt. But thing is that we'll always try to solve the time independent Schrödinger equations, and the solution of time independent Schrödinger equations give us stationary states, which have immense importance in understanding quantum mechanics. And in terms of the stationary states, we can discuss many things and also get the actual motion of the wave packet also, which is nothing but the time dependent solution of Schrödinger equations. With all this, ending up this video. Hope this video is useful for you. So thank you very much. Keep watching, please.